Hi, so far we have covered quite a number of examples related to the design of columns. Now we're going to talk about the foundations. As you know, there are two main types of foundations, which are the pad footing. Another one is pile foundations. Pad footing is normally used when the soil is relatively strong and the column is lightly loaded. It basically comprises a footing directly contact to the soil with relatively large contact surface area to the soil in order to distribute the stress due to the loading from the column to a stage that the pressure acting onto the soil to be less than the bearing pressures of the soil itself. On the other hand, pile foundations are normally used due to poor soil bearing pressure, that it will be unrealistic to have the pad footing acting onto the soil. It is either the contact surface area of the pad footing will become unrealistically large, or having the footing clashing into each other with the adjacent members. We have explained about various types of foundations as well as their applications in our previous videos about the reinforced concrete design too. To make it simple, under good soil conditions, pad footing may be used, whereas under poor soil conditions, when the soil bearing pressure is relatively low, you will need the pile foundations in order to ensure the stability of a structure. Now for this and the following videos, we're going to first deal with the pad footing. Similar to what we did in the columns, we will demonstrate the calculation steps for the pad footing under various circumstances. Here we outline at least 4 different cases that a pad footing can be designed. The pad footing may be subjected to pure axial loads without any moment. Also, it may be subjected to axial load plus the moment acting in the major axis, and then axial loads plus the moment acting in the minor axis, and also axial loads plus moment acting in both axes. We will use the same set of specifications in order to demonstrate the differences in terms of the calculations for the pad footing subjected to various circumstances. Here we will assume that the exposure class is XC2, where the member is subjected to coral attack, and most of the time the members is under wet conditions. We have the design life 50 years, and then the concrete strength, it will be 30. Unit weight of the concrete 25 kN per meter cube. Reinforcement bar with the FYK equals to 500 N per mm square. Soil bearing pressure 200 kN per meter square, and the maximum aggregate size equals to 20 mm. Assuming this is the pad footing, it is used to support a column with the size of 300 times 150 for all cases. The axial loads we assume equals to 1000 kN. In terms of the moment, depending on the circumstances, across the board, we will take 150 as the moment acting at the desired axis. Later in the calculations, since it involves the major and the minor axis, now we will have to standardize our understanding, where our definitions of the major and the minor axis, it will be defined as per the column. The longer side of the column will be considered as the major axis, whereas the shorter side of the column will be considered as the minor axis. Having this understood, Without further ado, let us get started. I use a spreadsheet to help me with the calculations. First, we deal with the pad footing subjected to pure axial load. The relevant specifications are included: exposure class, XC2, design life, either 50 years or 100 years. FCK, we use 30. For typical foundations, the FCK shall be minimum 30. Lower grade concrete is not recommended. Therefore, we will try using the foundations with 30. Unit weight 25. Steel grade we have 3 grades: 410, 460 or 500. In this case, we use steel grade 500. Soil bearing capacity 200 kN per meter square. Maximum aggregate size 20. Size of the column: the longest span HC equals to 300. The shortest span BC equals to 150. The ultimate load NU equals to 1000 kN. And then the design moment, it will be 0 for both axes. Assuming that we are using the 12 mm rebar for both main and secondary rebar, then we will proceed with the calculations. First, we need to determine the nominal cover. This is calculated using this equation, governed by the minimum cover plus the deviations. The minimum cover is determined by 3 components. First is due to the reinforcement bar. Second is due to the durability. And third, the minimum it will be 10 mm. The C min due to the requirements of bond is determined by the diameter of the bar, which in this case, the reinforcement bar proposed it will be 12 mm. That means the C min B it will be equals to 12 mm. And then we need to determine the C min durability. To calculate this, first we need to determine the structural class. The structural class by default is X4. And then we need to refer to table 4.3n to see if there is any changes in terms of the structural class. Our design period is 50 years. That means there is no changes in terms of the structural class. The concrete strength is 30. For the exposure class XD2, XD2 refers to this column, and then the strength class here. The structural class only changes once the concrete strength is greater than 40. In this case, the concrete strength is only 30. Therefore, the structural class will remain as class 4. And then refers to table 4.4n, XD2 structural class S4. The C min durability is equals to 40. That gives you 40 here. To determine the C min, we will choose the bigger value of the 3. C min B equals to 12. C min durability equals to 40. And minimum 10 mm. That gives you C min equals to 40. As for the deviations, the recommended value is 10 mm. That gives you a minimum nominal cover for the foundations equals to 50 mm. You will need this nominal cover for you to calculate the effective depth later. Next, we will need to propose a suitable size for the pad footing. Bear in mind that we are designing the foundations based on the prescriptive methods. It means that when we need to estimate the size of the foundations, it will be based on the serviceability limit state. And And then when it comes to the structural design, only then we use the ultimate limit state. Now that we need to estimate the size of the pad footing, we will need to get the surface load. However, in this case, the loading given is the ultimate load, where you have the factor of safety incorporated in already. The ultimate load given is a value only, giving you no informations how much of them coming from the GK and how much of them coming from the QK. We will need to do some conversions from the ultimate load into the surface load. Not knowing the quantum of the GK and the QK, we will assume that the effective factor of safety it will be equals to 1.4. Removing the factor of safety from the ultimate load, that means we're going to use the ultimate load divided by the factor of safety of 1.4. You get the axial loads equals to 714.3 kN. No moment acting onto the foundations. That will be the only load acting on the pad footing. We will need to include the self-weight of the footing. However, at this moment, we don't know the size of the foundations yet. Let us just assume that the self-weight of the footing is about 10% of the surface load. That means the total force acting onto the soil, it will be 1.1 times the axial loads. The axial load plus 10% of the axial load. Then we estimate the required contact surface area of the footing. This is done by dividing this 1.1 times the axial load with the soil bearing capacity, which is 200 in this case. The estimated area is equals to 3.93 meters squared. This will represent the recommended contact surface area of the pad footing with the soil. Based on this area, we can now propose a suitable size of the foundations. Since we only have the axial loads without any moment, that means square footing is recommended, assuming that the stress is equally distributed throughout the entire contact surface area of the footing. Let's say now we propose to use 2 meters times 2 meters length and width of the foundations. And then we can propose a suitable thickness of the foundations. For example, 500 mm or maybe 400 mm. At this moment, we are not really concerned about the thickness yet, because later we will need to go through the calculation steps to design for the moment resistance, work out the suitable amount of reinforcement bar to be embedded in the pad footing, and then checking the shear resistance of the member. We will need to check 3 types of shear. First, it will be the vertical shear at 1D from the column surface. It means that we are checking this shear plane, which is 1D from the surface of the column. Second, we will check the punching shear at 2D from the column face. That means we are checking this shear plane at the distance of 2 times the effective depth from the column face. And then lastly, we will check the punching shear at the column parameter. That means we are checking this shear plane surrounding the column perimeter. You need to make sure all the 3 shear resistance pass so that the pad footing is considered safe. In this case, if we use 400 mm, which is relatively thin, you will find the member fell in the shear at 2D from the column face. It passed the shear at 1D. and also pass the shear at the punching shear along the column parameters. That means the proposed thickness is insufficient. Now, if you are doing the manual calculations, you will need to start with proposing a thickness of the pad footing and then go through the tedious calculation steps. If you find the member fails in shear, you will need to increase the thickness of the pad footing. Since the spreadsheet tells that the thickness is insufficient, we shall straight away use 500 for the following explanations. Ultimately, we come to the proposed size of 2 meters times 2 meters times half a meters. Remember that previously we have estimated the required area of the pad footing, which is 3.93 meters square. Now the proposed dimension here will need to give you the contact surface area greater than this 3.93. It is only when the proposed area is greater than the estimated, then you may proceed. If not, no matter how strong you design the foundations from the structural side, the foundations will fail in terms of the stability. This you need to be careful. Once you have decided the dimensions of the pad footing, you can determine the actual self-weight of the pad footing. This is calculated by multiplying the volume of the pad footing with the unit weight of the concrete. Use this 2 meters times 2 meters times 0.5 meter times the unit weight, which is 25 kilonewton per meter cube. It gives you the cell weight equals to 50 kilonewton. Then we will need to confirm the soil bearing pressure is not exceeded. The equation used, it will be this. The bearing pressure is equals to the axial loops plus the self-weight of the pad footing divided by the area. Assuming the stress is equally distributed throughout the entire contact surface area. In the case that there is moment acting onto the pad footing, then you need to consider the effects of the moment based on my per I. In this case, we only have the axial loops, but we don't have any moment. That means, in order to determine the pressure acting onto the soil, we can exclude the effects of the moment. Not requiring the effects of the moment, actually you don't need to calculate the moment of inertia as well as the centroid locations as a result of the moment, which means you can ignore this stage. Simply take P equals to N plus W divided by A. The axial loops is the service load, which was calculated after dividing the factor of safety of 1.4, giving you 714.3 kilonewton, plus the self-weight 50 kilonewton divided by the contact surface area 4 meters square. It gives you the bearing pressure of 191.1 kilonewton per meter square. Compared with the soil bearing capacity, which in this case is 200 kilonewton per meter square. The soil bearing capacity is not exceeded. That means the proposed dimensions, specifically the width and the length of the pad footing, is adequate in this case. This covers the first part of the design of the pad footing, which you need to conclude a suitable size of the pad footing. Later, we will continue with the calculations of the moment at the ultimate limit state for the structural design, which we're going to discuss about that in our following videos. Stay tuned.